We are in section 8.3, Applications to Physics and Engineering. In the world of physics and engineering, there are many applications of integral calculus. We will look at force due to water pressure and centers of mass. Deep sea divers realize that water pressure increases as they dive deeper. This is because the weight of the water above them increases. So pressure is the force per unit area. So P equals F over A. Or we can say it's rho times G times D. So making a few notes over here, we know that rho, which looks like a P, is the density of fluid. Which is going to be, units would be kilograms per mass cubed. And we have D in our formula also, which is just the depth below the surface. So depth below surface. And G, which is that gravitational pull. So we have 9.8, and this is meters per second squared. And then we also have delta, which is going to be equal to our weight density. Which is the same thing as just rho times G. So another way to look at that. And so one more thing to kind of write down here from before was that a Newton, which is 1N, is equal to, and our units were kilograms times mass over second squared. So the units for pressure are going to be 1 Newton per meter squared, or 1 Pascal, or written as kilopascals, depending on the size. So at any point in a liquid, the pressure is the same in all directions. Therefore, P is equal to rho times G times D, or delta D. And what we have also is called hydrostatic force. So hydrostatic force, which is going to be F equals P times A. This is going to be pressure and area. And this is a force exerted by a fluid at rest against a vertical plate or wall or dam. The pressure is not constant, but increases as the depth increases. So again, hydrostatic force is force exerted by a fluid at rest against a vertical plate or wall or dam. The pressure is not constant, but increases as the depth increases. So the first example we have here says a tank is 8 meters long, 4 meters wide, and 2 meters high, and contains kerosene with a density of 820 kilograms per meter cubed to a depth of 1.5 meters. Find part A says find the hydrostatic pressure at the bottom of the tank. So again, pressure. And so in order to do this, the first thing I'm going to do is just sketch what it is that we're dealing with, which is a tank that's rectangular, it looks like, that's 8 meters long, 4 meters wide, and 2 meters high. So our tank is 8 meters long, 4 meters wide, and 2 meters high. So sketching that quickly just to kind of get an idea of what we're dealing with here. And so part A is asking for the hydrostatic pressure. And so our pressure is given from above. It's going to be rho times G times D. And we know that rho, that density of the fluid for this problem, is 820. And the units are kilograms per meters cubed, times G, which is 9.8 meters per second squared, times D, which is that depth And for this one, it tells us it's 1.5 meters. And so working this out, we get 12054. The units are going to be kilograms per meters second squared. And so this from up above, this is by definition what a Pascal is. And so this is going to also be the same thing as 12,054 pascals. Or if you wanted to write it in kilopascals, you can. So this would also be equivalent to 12.054 kilopascals. So either of these answers is okay to have. Part B says find the hydrostatic force on the bottom. So part B is the hydrostatic force, and we know that force is equal to pressure times area. And so the pressure we got from part A is 12,054 pascals, and that area on the bottom, so the area that we have on the bottom of our tank, which would just be 8 times 4, which is 32 meters squared. And so multiplying this out, and again remember pascals, the units are written right up above. And so when we multiply this out, we are going to get 3.86 times 10 to the 5th. The units, when you simplify those, are going to be kilograms times meters per second squared. And we had written up above that by definition this is equal to a Newton, so this would be equal to 3.86 times 10 to the 5th newtons. Part C says find the hydrostatic force on one end of the tank. So this one's on the end, part B was on the bottom. And so part C, this on the end, if you think about this, I'll go ahead and look at this end on the right if I were to shade this. And it's different. So that force is going to be different at the bottom as it is going to be on the top. And so pressure changes as the depth changes. So we'll go ahead and write that down. So pressure changes as depth changes. And so we're going to use our calculus knowledge and go ahead and set this up with a little rectangle here. So I'll go ahead and put my little rectangle on there. The area of this little rectangle that we have right here is going to be, and we'll call this little width delta x, is going to be 4 times delta x to figure out that area. And so we'll call this area of the small rectangle, or that strip. And so as we talk about our pressure for this, this is equal to rho times G times D. And D is changing, so depth changes. So keep that in mind. So we know rho, it's still dealing with the kerosene, so that's 820 kilograms per meter cubed. G is still the 9.8 meters per second squared. And the depth changes, and since we're dealing with something that changes, we're going to go ahead and call that depth there x. So we'll say that's x meters. And so working this out, we get 8,036 x pascals. And so in order to find that, the hydrostatic force at the end of the tank, force equals, so since we're dealing with this change, we're going to have an integral. I'm going to go ahead and put our pressure formula down, which is 8,036 x. then times that area of the strip, which is going to be 4 times delta x, which in this case we'll write as dx. And we're integrating over that depth, which would go from 0 to 1.5. And so rewriting this, we have 8,036 times 4, which is 32,144, times the integral of 0 to 1.5 of x dx, which is now going to be 32,144 over 2 times x squared, evaluated from x equals 0 to 1.5. And so substituting this in, we have 32,144 divided by 2, which is 16,072 times 1.5 squared, minus substituting in 0 is just 0. And then evaluating this, we get 36,162 newtons. To find the center of mass, or the center of gravity, or the centroid of a thin plate of any given shape is to find the point P such that the thin plate balances horizontally. So it's almost like if you were to take an object and just set it on your finger, you need to find that centroid, that center of mass, where it would balance exactly. And so you can see that in the picture there, it's x bar comma y bar was that point. And so dealing with two masses in the picture next, we would have to figure out where mass 1 times distance 1 is equal to mass 2 times distance 2 to make those equal. In a system of particles M1, M2, M3, and so on to M sub n, located at the points, and we have x1, y1, x2, y2, and then all the way through x sub n, y sub n, in the xy plane, then, I'm going to go ahead and give this a star, the moment of the system about the y-axis is going to be equal to m sub y equals the sum from I equals 1 to n of m sub I times x of I, and the moment of the system about the x is going to be equal to m sub x, which is the sum from I equals 1 to n of m sub I times y sub I. And then the center of mass that we have, which we're going to call x bar comma y bar. X bar is going to be m sub y over m, and y bar is going to be m sub x over m, where m is equal to the sum of m. So now suppose that the plate is a region bounded by the curves f of x and g of x on the interval from a to b. So we want to find the center of mass of the region. If only one function is given, then g of x is going to be equal to 0. So next, we need to find the moments of the region, which measures the tendency of the region to rotate about the x-axis. This is denoted m sub x, or the region rotated about the y-axis, which is denoted m sub y. So the next thing we have, give those formulas a star, are moments about the x-axis. And we have two integrals given there, one for a moment about the x-axis and moments about the y-axis. The coordinates of the center of mass x bar comma y bar are given the next box, and so the centers of mass of those coordinates, and where a is given as the integral of the difference between f of x minus g of x dx. So note that the density, rho, of the plate cancels out, so it isn't really needed. So the first example that we have says the masses m sub I are located on the points P sub I. Find the moments m sub x and m sub y and the center of mass of the system. And so for this one, we're given 4 points and masses with those. And so in order to do this, to find our m sub x, this was equal to the sum from I equals 1 to n, which in this case we have 4. And it's m sub I times y sub I. And then to find our moments about y, we're going to do the same thing with the sum from I equals 1 to 4 of m sub I x sub I. And so for the first one, the mass is 5, and the y value there is 2. Plus the next mass is 4, the y value is 5. And likewise for the other two, we have a mass of 3, y value of 2, and mass of 6, y value of -2. And working this out, we get 24. Likewise, for m sub y, we have the sum of mi xi. So the first mass is 5. First x value is -4. The second mass is 4, and our x value is 0. The next one is 3 times 3 and 6 times 1, which works out to be -5. And then in order to find that center of mass, which we called x bar comma y bar, this was equal to m sub y over m and m sub x over m. This is where m, lowercase m, was equal to the sum of those masses. So I equals 1 to 4 of m sub I, which is going to be 5 plus 4 plus 3 plus 6. And so this works out to be an 18. And so the center of mass, x bar, is going to be m sub y, which is -5, over m, which is 18. And our y value, y bar, is going to be m sub x, which is 24, over lowercase m, which is 18. You can simplify y bar. So we have -5 over 18, comma 4 over 3. And so if you were to think about this with a graph, and I'll do this quick little graph down here, and if we were to plot all of those points that we have, those 4 points that we have here given, we would have -4, 2. We have 0, 5. We have 3, 2. And 1, -2. And so those are our points. And if you think about our center of mass, which is at -5/18, 4/3, say about here, this is going to be our x bar, y bar. You can see that that is in the center of that mass that we would have between all those points. And those weights that are, those masses that are at each of those points is different. Again, mass 1 is 5, whereas mass 3 is 3. But that center point where you could balance it would be at that x bar, y bar. So we have another example right below, which instead of it being points, it's going to be now a region. And so this example says, sketch the region bounded by the curve and visually estimate the location of the centroid. Then find the exact coordinates of the centroid. So this time we're dealing with a region. And the region that we have says y equals 2x, y equals 0, and x is equal to 1. So let's go ahead and sketch this. We know x goes out to 1. And substituting a 1 into that first equation, 1 times 2 is 2. That large y value that we'd have would be 2. And so at 0 we have 0. At 1/2 we would have 1. And at 1 we would have 2. And we have y is equal to 0. And we have x is equal to 1. And so this is our region here, this triangle. And so the first part does just ask for you to estimate it just by looking at it. So where would that center of mass go? Clearly it's not going to go on one of those edges of the triangle. So I'm going to estimate it to be somewhere maybe around here. And I'm going to call that x bar, y bar. Now it says to actually find it, the exact coordinates. And in order to get x bar, since we are dealing with the region, the formula on the previous page was 1 over a times the integral from a to b of x times f of x minus g of x dx. And so the area that we need to find, and I'll write that down here, is going to be the integral from a to b of f of x minus g of x dx. And so we are integrating x from 0 to 1. That top function that we have is 2x. G of x would be that bottom function, which is 0. dx. And so we have the integral from 0 to 1 of 2x dx, which is going to be equal to x squared evaluated from x equals 0 to 1, which is just going to be 1 minus 0, or 1. So x bar, again, is equal to 1 over a. We just found a to be 1. And then we have the integral from 0 to 1 of x times 2x minus 0. We just did that down below. And simplifying this, we have the integral from 0 to 1 of, it's going to be 2x squared dx. And then integrating this, we get 2 over 3 x to the third, evaluated from x equals 0 to 1. And this is going to work out to being just 2/3. I'm going to underline that just so we keep track of it. Next, we need to find the y-coordinate for our center of mass, or y bar. The formula on the previous page was 1 over a, the integral from a to b of 1/2 times f of x squared minus g of x squared dx. And so from here, we know that a, our area, was just equal to 1. We have the integral from 0 to 1 of 1/2 times, and then we have 2x squared minus 0 squared dx, which is going to be 1/2 times the integral from 0 to 1. And we have 4x squared minus 0, or just 4x squared dx. And we can simplify this a little bit more, pulling that 4 out, and we're going to have 2 times the integral from 0 to 1 of x squared dx. And integrating this, we get 2/3 x to the third, evaluated from x equals 0 to 1. And so substituting in 1, we get 2/3 minus 0, or just 2/3. So this is our y value. So x bar, y bar, centroid, that center of mass, is going to be equal to 2/3, comma 2/3. And again, this is our centroid. So 2/3, comma 2/3 looks about where we stuck our x bar, comma y bar originally on our graph, where we estimated it on that region. So we have one more problem to do. The next example, we'll go ahead and circle that, and we will do this one together in class.